record.
Yeah, and if someone's sick or something.
If someone were not.
Okay, I'm recording on your computer.
Okay, should be fine.
All right.
Good morning. Want to do some scattering? Yeah. All right, I haven't met all you guys, but I'm really happy to be here to do some lectures on scattering. Just a little bit about myself. I'm actually originally from Maine. I did my PhD with a manual in ocean optics, focused on IOP measuring, methodology, and looking at scattering from aggregate. I kind of ended up in oceanography in a strange way. I was actually getting my master's degree in electrical engineering, working on a problem that I had. It happened to be a remote sensing algorithm for ocean color, and I had no idea about ocean optics. And I ended up with this giant spreadsheet of numbers that apparently oceanographers had taken, years to accumulate 50 numbers, and it just blew my mind that we didn't have the data to build these algorithms. Fast forward 15 years, 20 years, or whatever it is, and now we're just so inundated with data and measurement capabilities. It's just absolutely incredible. But ever since sort of seeing that first that first data and how the measurements were made, I was just totally fascinated by the process of making these measurements, and the engineering side of me just was really, really keen to kind of continue that after grad school. So I took a position at Sequoia Scientific out in Bellevue, Washington, doing instrument development and scattering measurement development. So this is sadly not the view from my office, but it's a really cool picture. I didn't take it either. It's clip art that I found on the web. But it's a pretty striking picture, right? What looks cool about this picture? Right? Colors. So like there's all sorts of colors happening. There's reflections off buildings, right? There's diffusion of the sunlight through things. Like what's causing that? Is it absorption that's causing all of this stuff? No, it's scattering. What happens if we don't have scattering? The sun's just a little white blob, right? It's absorbed directly by the atmosphere in some ways with molecular absorption, but ultimately we just see the direct rays from the sun. And this slide idea is something I totally ripped off from Kurt Mobley, where he demonstrates Mobley's law of optics, which is if the light doesn't reach your eye, you don't see it. And ultimately, scattering is pretty much what gives us the picture of the world that we see, or what gives us the striking visuals. You saw some aspects of this when you were playing with light in the lab the other day, right? If you don't have scatterers in the water and you shine the laser pointer in, you don't see the light, or maybe you see the faintest little bit because of impurities in the water or scattering from the water itself, right? But the minute you add Malox or some scattering agent, you see tons and tons of scattering, right? And when you were playing with the polarizers in different positions and looking at the beam in different ways, you could see even more changes in the beam and what you see. So there's a lot of interesting physics going on that go from getting that laser pointer light to your eye through polarizer. And that's roughly what we're going to talk a little bit about today. So Meg gave an absolutely incredible overview of absorption and the physics behind absorption. So that's one way that light interacts with matter in the ocean. Removal of photons, conversion of energy to molecular energy, thermal energy, fluorescence, all these quantum things that Meg was talking about. Really interesting. What else is happening in the water, right? There's a whole other world of scattering. That's the change in direction or the wavelength of a photon when it interacts with matter. The basic idea behind pretty much any scattering is that it's an interaction of a light wave with a heterogeneous medium. that medium, that matter, is composed of discrete electric charges like protons, electrons. It could be atoms, it could be molecules, it could be giant particles, but it's ultimately matter is all just E's and P's. So that that matter, that obstacle, that it could be a molecule, it could be a single charge, it could be a giant particle. We put that in an electromagnetic wave, and no matter what the heterogeneity is, whatever the scale is, ultimately the scattering comes from the interaction of that wave with those charged particles. In any scattering, what is happening is that the wave is moving those particles, moving those dipoles. We'll look at it a little bit more deeply later, but those charges are then going to re-radiate electromagnetic radiation. And it's that secondary radiation that we refer to as scattering. That secondary radiation could change wavelengths. Meg went through several phenomena that cause a change in wavelength. We call that inelastic scattering. That I'm not going to talk about today. I'm going to talk about elastic scattering, which is just a change of direction. And then there's another kind of easy formula to think of. Scattering is excitation of that medium, then re-radiation of energy from that medium. Just very general definition. Does that make sense? Right. Yeah. Elastic scattering is going to be all the same. The re-radiation will be the same frequency. So in the same media, it will be the same wavelength. All right. I also stole Meg's slide, sort of giving you the overview of week one to just kind of, I think a bunch of us are stealing Meg's slide for this to give you an idea of where we're at and where we're headed this week. So today and tomorrow we're doing scattering. I'll do 2 lectures on scattering. Manuel's doing electron beam attenuation, and I think Meg's doing electron particle size. They're all kind of connected together, so you'll hopefully hear a lot of the concepts and similarities between the concepts across several of these lectures to reinforce the ideas. Tomorrow, we'll do a scattering and beam attenuation lab. So we'll do some of the same sorts of things that you did with absorption yesterday and today, with different sensors that measure scattering and absorption. So today, the big picture sort of things that I want to cover are defining and measuring scattering. So what do we use as physical quantities to discuss these phenomena? A little survey of the theoretical side of what causes scattering. And then connecting those physical properties and processes to what we actually measure. And like absorption and all the quantum stuff, this can be looked at in incredibly, rich detail with a number of different physical approaches. This is meant to just be a survey to give you some of the words and language to be able to look up what you need. Tomorrow we'll continue a little bit with some methodology of how you measure scattering, and then look at some examples of scattering by different particles and substances and phenomena in the ocean. And then just look at some of the issues and interesting things that are current topics of scattering. So reinforcing that, so today again, we'll look at scattering as an inherent optical property. Meg got after absorption a little bit yesterday, looking at the Beer-Lambert-Bourget law. We'll talk a little bit more about that in terms of scattering. We'll look at what scattering is, sort of in terms of some of the processes in physics you might have had in undergraduate or even high school physics. We'll look at what properties of particles affect the scattering through those phenomena. And I'll give just a little bit of a taste of a whole new world in scattering that we're looking at these days, which is polarization. And then tomorrow, like I said, we'll look at measurements, we'll look at examples and some of the oddball things, a potpourri for the Jeopardy fans. All right, so why is scattering important in the ocean? Colin went over several things in her first lecture on the radiative transfer equation. What parts of that, which of the case studies, for example, would you say are important in terms of scattering? She had 2 case studies, right? One was all absorption, no particles, and one was particles and no absorption, right? what were the takeaways from that? Yeah, I mean, that's pretty good summary, right? If we don't have scattering, no photon's going to make it to our ocean color sensor, right? That's ultimately why one of the biggest reasons scattering is important in the ocean for us at Ocean Optics Lab. So not only ocean color remote sensing, but any sort of propagation of light within the water is going to encounter scattering through the radiative transfer equation. It's a major component of that calculation. Few other things. When you scatter within a medium, you're increasing the effective absorption by increasing the path length. So as you're scattering, you're increasing your path length through the medium and giving those photons more of a chance to be absorbed. That's one thing. I think Meg talked a little bit about the like integrating cavity measurement. So that's a case where the scattering off the walls of the integrating sphere give you more path length within that medium. Coming later this week and next week, there's a lot of different ways you can use measurements of scattering to tell you something about particle composition and what's in the water. So what we call proxy measurements. And so that's a whole other lecture in itself. And then a third thing, which I think is just kind of neat visually, is it degrades underwater visibility. And so these are two different cases where scattering is affecting underwater visibility. So there's a hydrothermal vent over on the left, and what one could assume is probably like coastal New England or something on the right. What's different in these two scenarios? They're both scattering, I'll give you that part. What's scattering in these two different scenarios? Any idea? The right one should be pretty straightforward. Perfect. Yep, exactly it. So particles or density difference, different physical things, but similar physical models, right? So each are going to scatter light waves. So scattering occurs in three places in the ocean. At the air-sea interface, you've got transmission of the sunlight coming through the ocean, or a LiDAR going through the surface of the ocean, and some of it gets refracted through the ocean, transmitted, if you will. Some of it gets reflected back up. There's the sea bottom, so if you have any sort of light that's impinging on the bottom, like a shallow water ocean optics scenario, you would have light coming off the bottom. And then within the water column, so the water itself, particles, turbulence, bubbles, all these different things that are in the water column are going to scatter. And that's what we're going to focus on. Again, all of these different scattering, whether it's the bottom, air-sea interface, or in water, are the same physics. We use a lot of different words, a lot of buzzwords: Rayleigh scattering, Mie scattering, surface scattering, volume scattering. All of these things are fundamentally interaction of light waves with charged particles, whether it's a molecule, a particle, or just a random electron. But depending on those scales, so if it's a large particle versus those density fluctuations, we can use different physical models. So the math looks a little different, but ultimately you'll see a lot of the same concepts when you dig deeper and deeper into scattering. You'll see a lot of Bessel functions, you'll see a lot of signs and diffraction and all these sort of formula that you get in like undergraduate physics. I'll talk just a little bit here, going broadly over inherent optical properties. I just wanted to point out this paper. It's a really interesting read. For like as somebody who works with instrumentation and I guess is sort of in Van Veld's academic family through Emmanuel. This is a paper. So Ron Zandeveld was one of the co-founders of Wet Labs, developers of AC instruments, transmissometers, all sorts of things that we've used in ocean optics to transform the field. And before that, lots of work also in just theoretical ideas of ocean optics. So this is a great read, great story about his journey in ocean optics. So I think it's pretty inspiring. But inherent optical properties are the scattering, the absorption coefficients and such in the water that don't depend on the ambient light field. So they're just depending on the material dissolved, particulate, or the medium itself, like water. So we can think about inherent optical properties by sort of starting with an elemental volume, kind of like how we derived Beer's law yesterday. Except in this case, we'll look a little bit more generally. So you have an optical power or some radiant flux coming into the volume. So we'll call that phi sub I. That's watts, the power. And then we'll have a certain amount of watts that are absorbed in the volume. So that's phi sub A. We'll have a certain amount to make sure that's transmitted through, phi sub T. And then there's this phi sub S, which is just the amount that's scattered. What does conservation of energy tell you about this elemental volume? Like what's going on here? Are there any sort of broad ideas?
What you put into the box, you get out.
All has to add up, right? Yeah. The incoming flux has to equal the outgoing through absorption, scattering, and transmission. And Meg went through absorptions yesterday. We'll talk a lot more about scattering today. So that's just that same fraction of scattered power or flux related to the incident. So it's unitless. Transmittance is just the sum of those two. Again, that's just an expression of conservation of energy. In looking at the IOPs, we're usually concerned with what we call the coefficients, so the absorption and scattering and attenuation coefficient. Here we can start with that scattering, so B, the phi S over phi I, so that fraction, unitless fraction. If we imagine our volume has some vanishing path that it's representing, then the amount of light that's being scattered, or what we call like the differential scatterance or the delta B, is getting increasingly small. So we can look at that as calling, the limit as delta R goes to 0, or we could just look at it as the derivative. But that's where we get our inverse meter units for all of our IOP coefficients. So we tend to work in B's, in lowercase b's, not uppercase b's, because we need the context of that path length really to do a lot of that, to do our biogeochemistry or radiative transfer measurements with. Yeah, and B sub lambda, or B as a function of lambda wavelength. So pretty much everything that I'll talk about today has a wavelength dependence. Sometimes we get sloppy and we leave out our notation, whether it's angle or wavelength. But generally, almost everything is wavelength dependent. And the scattering coefficient is just a measure of the total scattering. It doesn't tell us anything about the angular distribution, right? Just the sum of all that phi sub S. So we talked for the angular stuff about the volume scattering function. And this is just a really general version or formulation of that, where we have some incident beam and irradiance into a sample volume. Here I just have it propagating along some axis z hat. We get some amount of light that's scattered out of that delta D, or dB, sorry. And it's scattered within a certain solid angle. You guys, are you familiar with solid angle? Thumbs up, thumbs down, thumbs side. So it's stayed within some solid angle, and it's a certain intensity. So intensity is just the flux or watts per steradian, or per solid angle. The definition of volume scattering function is just a proportionality factor between the intensity that's scattered out of that volume to the incident irradiance. So it's just a proportionality factor. And really generally, if we think about this direction xi, could be arbitrary. We're not talking just within a scattering plane or any sort of symmetries. It's just beta xi, beta some direction at some wavelength is that proportionality. Units, so watts per steradian for an intensity. Irradiance, watts per square meter. And then the dB, the volume, if you work that all out, you get per meter per steradian. So that's the units of the volume scattering function.
Can we describe it out? So I have already come down.
Oh, we'll get there. All right. Yeah, so we'll talk solid angle in just a minute. Basically, it's, if you have a plane angle, which we're all used to when we think angles or radians, degrees, you've got some angle, right? It's two lines, it's the angle between them, it's the ratio of the arc length to the radius of that circle, right? So with sphere, it's a little different. It's the area rather than the arc that's subtended by you could think of it as a cone, but it doesn't have to be a cone. It could be any shape coming out of the center of that sphere to the outside of the sphere. I have a graphic of that shortly. But it's the ratio of that area to the radius squared. And that's just by definition, it's like plane angle is arc over radius, solid angle is area on the sphere over radius squared. It'll make a little more sense in the picture when we start looking at what that actually means. But before that, in ocean optics, we don't typically work with that very general Xi scattering direction. We look at a case where it's sort of spherical coordinates, so we look at the polar and azimuthal scattering angles. And so here you've got your incident beam coming off of this angle here, and it's in some polar scattering angle psi being scattered, and then with that angle fixed, you can still trace the circle here. And this would be the azimuthal angle. So the azimuthal angle is defined from, I think, the XZ plane positive down. So azimuthal angle, polar angle. For unpolarized scattering, for unpolarized incident light and particles that are randomly oriented within a sample volume, there's a symmetry that we can take advantage of where the shape of the volume scattering function is azimuthally symmetric. So typically when you look in ocean optics literature, you'll see things as beta psi, not beta psi and phi, because the azimuthal dependence is not ignored, but we don't have to keep track of it. There's the symmetry. And so that polar scattering angle psi, that's what, when you look at a VSF or you pull up look at Petzold, like we'll do here in a second, that scattering angle is psi. Some people call it theta. Different people have different conventions. Sometimes theta will mean it's the polar angle in like the global coordinate system, but then scattering angle is if your beam is going in some arbitrary direction, it's the polar scattering angle from that beam. So you just have to kind of keep track of nomenclature and be kind of fussy about making that all consistent. So these are some examples of volume scattering functions. These are the Petzold phase functions, the volume scattering functions. These were measured in the 70s. Back in the early days of ocean optics, people built their own instruments to measure things. These measurements were measured in a very limited range of environments. San Diego Harbor, I think the clear waters of the Bahamas, and like coastal California. So not a huge range of conditions. They made these measurements combining two instruments. There was one specific instrument called the LASM, the low angle scattering meter. Custom instrument, made out of light bulbs and giant pieces of steel. And that made very near forward measurements, not terribly unlike what you would get out of a Sequoia list instrument. And then the GASM, which was the general angle scattering meter, and that's just some sort of like prism apparatus that looks at the wider angle scattering. So they combine those two. You'll note, so I've plotted it two different ways. These are from the Ocean Optics book, which is a fantastic resource. So the VSF, just in general, its magnitude varies a couple of orders of magnitude across all angles, and then for all VSF across all angles, and then any given VSF itself is 6 or more orders of magnitude. So one scan of a VSF, if you will, covers 6 orders of magnitude. Having to cover those 6 orders of magnitude while also the magnitude of the whole VSF is changing are major instrumental challenges. Making a VSF instrument is really tricky stuff. But these were from the 70s. These are like canon in ocean optics. These are the most common, these are the most popular. But we'll see they maybe have some issues. They're not issues. They have limitations and they're often misused. So scattering coefficient. So we derived it from just the argument of that sample volume with a certain amount of scatterance and the volume getting small. The other way to think of it is that we could integrate the volume scattering function over the entire sphere. So we would say that is B is equal to the integral. This notation there is just denotes the whole sphere of beta xi d solid angle. That's just the definition. That's just showing that we're going to integrate the DSF over the whole sphere. So we know that we can call beta, we can relate beta to just the scattering angle, right? So we can get rid of the azimuthal dependence and think about it much simpler that way. But the d omega is a little bit of a tricky thing to think about, unless you work in spherical coordinates all the time. So solid angle, so again, plane angle, you've got just a circle, you've got some arc, circle has a radius, plane angle theta in radians is just the arc length over r, basic geometry. If you think about that, that arc length, circumference of a circle, so the full arc length of a circle is 2 pi over r, 2 pi r, and then for a circle of radius r, it's r. So your total amount of radians or angle in a circle is 2 pi. That's hopefully familiar. The analog with solid angle is that you've got some misshapen blob of area on the outside of a circle that has radius r. And you know the area of that blob. So if you take the area of that blob and draw, a cone or whatever sort of surface you need to get back to the center of the circle, the region, I guess, if you will, that's subtended by that area is omega. That's a solid angle. And so, like I said, it's that area divided by the radius of the circle squared. So thinking about what the surface area of a circle is, 4 pi r squared, radius is r squared. So in this case, you have 4 pi steradians. So in a circle, you have 2 pi radians of angle. In solid angle, you have 4 pi steradians of solid angle. So sometimes in this integral here, like where I use the weird symbol, I forget what it is there that Mobley uses, sometimes people will put 4 pi there just to symbolize that you're integrating over the entire solid angle. So thinking about the differential solid angle, so that d omega, this is tricky. It's tricky to draw, it's tricky to explain, and can be tricky to understand. If we imagine a unit circle, not a unit circle, a circle with a sphere with radius r, where we have some patch of area. And we're looking at that patch in terms of spherical coordinates. So we're gonna have that patch at a position that's theta from, at polar angle theta and azimuthal angle phi. This definition of typical spherical coordinate system. And we're looking at a differential area here. So there's a d theta that's making this little box here, and there's a d phi that's making that box. So if you think about that area, just based on the definition of solid angle, it's r squared times d omega. Thinking about it in terms of two sides of not a rectangle, but I guess as you're getting infinitesimally small, it's a rectangle. You've got an arc length in this direction here that's r d theta. So you've drawn a circle here on the sphere that goes all the way around the sphere. It divides it into 2 hemispheres. Radius is r, and the distance here, or the angle, the angle is d theta. So that side right there. And so we look at our dA, we have the first side, which is r d theta. So that's a solid angle. And then if we think about the other way of making a hemisphere here, similarly, that would be radius r and d phi. So d phi is that distance there, right? Except here, we're drawing a circle it's more like a polar cap. It's a latitudinal ring on a globe. It's not the full radius of the sphere. So if you do the trig here, if you draw a little triangle here and figure out what the radius of this polar circle is, it's sine theta. this basic trait. And so this area then similarly is r sine theta d phi. Does that make any sense? It's tricky if you don't work in spherical coordinates much. But ultimately it comes down to you're making an area from the lengths of two sides. Each of those sides is an arc length. One of those two arc lengths is straightforward. It's this r d theta, because it's an easy circle. It goes all the way around the sphere, and it's straightforward plane angle, or from the plane angle formula. The other one has the sine theta because it's not dividing the sphere into two hemispheres. It's a polar circle. So that, again, that other side is the r sine theta d phi. So our dA is r d theta r sine theta d phi, which if you simplify it and figure out, now we can solve for what d omega is, sine theta d theta d phi. Keep that in your pocket. All right, so we didn't have an expression for d omega. Now we do. D omega is sine theta d phi. So there's this tricky business in going to our standard expression of scattering coefficient where there's this sine theta factor or sine psi factor. And it's kind of confusing at times, but it comes from that solid angle and that integration across the whole solid angle. So if we do the integration of beta phi, psi phi, with our expression for d omega, we get this azimuthal symmetry. So this guy goes away. This guy integrates out 0 to pi. So we have a 2 pi and beta phi sine phi d phi psi. That's just sort of the basic thing you'll see typically as an expression for scattering coefficient in oceanography. Relating that to attenuation, so we had our basic definitions of IOPs, A plus B equals C. So B could also be thought of as the attenuation minus the absorption in terms of coefficient. And then one other IOP I'll throw in here just for reference. If you ever do Monte Carlo, this one especially pops up, just the single scattering albedo, so the probability of photon survival. So it's the probability that something is scattered related to the total amount that's attenuated. Okay. Two other things for the scattering coefficients. There's two other ways we often look at that. We can not do the whole sphere. We can look at the forward scattered light. So what goes into the forward hemisphere compared to your incident beam, and the backwards hemisphere. So looking at just the plot of BSF, that's roughly, it's basically equivalent to integrating from 0 to 90 for the forward scattering, 0 being near forward, it's where your beam is headed. And then back scattering would be from 90 to 180. 90 to 180 right here. And that's the back scattering. That's good stuff. Everybody likes that. Backscattering ratio is another quantity that gets kicked around in looking at scattering. That's just the fraction that's backscattered related to the fraction that's related to the total scattering. Here I'm showing it as BP, so the particulate backscattering ratio. So the amount of particulate backscattering related to the total particulate scattering. I think Meg or Emmanuel will be talking a little bit. That's often used as a proxy for index of refraction. So this is one of those cases where based on the shape and the qualities of the scattering, we can get information about the particles in water. As just a parameter to quantify the relative strength of backscattering, it's starting to be used a lot more in looking at radiative transfer models for remote sensing, where you can be more precise about the light field underwater by considering the shape of the light field, like how much is being scattered forward versus how much is being scattered back. Phase function. So phase function pops up a lot. This is just the idea that we factor the VSF into the product of the scattering coefficient and then some what we call phase function that has the angular information. So we typically throw a tilde on top of beta, and it's just VSF divided by beta. this integrates up to pi. Works out well. This is an example of some phase functions from those same Petzold measurements. You see they collapse down. It gives you a little bit better idea of like what the overall typical shape of a VSF in the ocean is. It's very highly peaked in the forward. You know, again, we have 6 orders of magnitude in variation there. From the different environments, so turbid harbor, coastal ocean, clear ocean, you can see there's a little bit of a shape difference. So one is higher, one's steeper than the other. So there's some differences there. So this looks pretty good. This looks like a good approach for Petzold, but it's always important when you're thinking about phase functions or using Petzold, keep in mind the limitations of the data, the limited environments that it was considered for or measured in.
How we about that previously? Can you just explain how you read it?
How you read it?
Yeah, what is the meaning of that?
Sure. So this is just the log space. So the scattering angle, zero scattering angle is towards zero scattering angle is being scattered in the direction of the incident beam, right? And then 180 is scattered perfectly backwards.
Okay, so
Yeah, very much. We'll see some pictures of like looking at polar plots where you can see it's very, very near forward. Yeah, so you'll typically see these at least log on one axis because there's a huge dynamic range. So, you know, this looks fairly smooth and not that steep, but when you consider that it's covering 6 orders of magnitude over angle, it's pretty steep. Does that make sense? Is that what you were thinking? So here's an example of some BSF or phase function measurements. So these are from a volume scattering sensor that was deployed a decade or 2 ago up close to New Jersey. The same instrument. There's a few of them out there. They've been used to generate a lot of phase functions in BSF. It's called the MVSM, multispectral volume scattering meter. So this might have been just the VSM, as in it's not multispectral. So this was, I think, 60-something measurements close to New Jersey. You see that same sort of steep near forward structure, so a lot of scattering near forward. But when you look at the phase function towards the back, you see there's a ton of variability there. There's an order of magnitude in phase function in these back scattering angles. And the red line there is the Petzold average. So you can see that on average, Petzold looks pretty good. But you probably have, especially if you're looking at backscattering, an order of magnitude of uncertainty if you haven't measured your own phase function or used a better model. What do you think's going on there? It's a trick question. I think it's probably related to an instrument artifact. The way this instrument works, it has a hard time getting at angles very close to the backscattering direction, which is not uncommon in volume scattering sensors. Sequoia makes a volume scattering sensor, and it only gives data out to about 150, just based on geometry. We'll go over that a little bit tomorrow. But I throw this up here because if you just received these data from a colleague, you got to be skeptical. You've got to think about it. You've got to think, does it make sense that it has those bumps and wiggles towards 180? So always something you got to keep in mind. Be skeptical. Okay.
I wanted to look into figure a little bit more.
Sure.
So what this is telling us, the phase function is scattering behavior of angular scattering behavior of a medium.
Yeah.
And so how does that relate to the environment? Like, so basically, why should we care?
Yeah, there's 2 big reasons. 2 reasons. So one is if you're doing remote sensing, ocean color remote sensing, right? So you're using the radiative transfer equation, hydrolight, something to try to model the behavior of light that's coming down from the sun. So the phase function is like the first order description of the shape of that, first thing that's going to go into the shape of that light field. Right, so if the phase function is more near forward, you're gonna have more scattering down before you have scattering back up towards the surface. Does that make sense? So phase function in radiative transfer calculations and things like that are pretty important. I'm by no means a hydrolite expert, but you know, in hydrolite, I think Kurt Manuel, I think you were on the paper, like you looked at the effect of choosing different phase functions in hydrolite or radiative transfer calculation, and there's huge differences. He had some measurements of remote sensing reflectance compared with hydrolite simulations, assuming different phase functions, including Petzold, some pretty crappy ones, and then measured phase functions. And there was a huge difference in the simulated reflected spectra that you got out. And knowing, using the right shape of the phase function mattered quite a bit. So that's one reason, shape when you're doing radiative transfer calculation. The other thing is, if you have sensors where maybe you're not doing it from space, but you just have some sort of angular scattering sensor in situ. We can come up with ways potentially where this shape might depend on properties of the particle. So it turns out that the sort of steepness or the ratio of backscattering to total scattering, or the shape of the phase function, is related to the index of refraction of the material, or the particles that are in the water. That's a crude way of saying it, but we can use the shape information as a proxy for something about the water. Those are the two reasons I can think of. Any more?
I mean, it's a critical piece when we are trying to do an exercise in closure with measurements of light and measurements of light. You want to know whether I need to make sense. One of the approaches is driven to the beyond measurement. Wayne said, going from either these to then going to the color of white, or vice versa, and to check that consistency is absolutely critical that you have the right for the. If you don't, they're not going to do. And it tells you a lot about it's closure business that is bringing into your head. It will tell you a lot about the uncertainty of your life. Now, why don't we do the it all the time? Because when we measure the space, most of the thing was the atmosphere. Even knowing whether we moved it correctly, when we extrapolate it, is something that there's still a lot of debate to do. What is really expect. And then by comparing it to what we have in the water, it goes back to, can we say something about more of the related space? What are the uncertainties that are in this whole chain of events that we're making measures somewhere in space, or we're going to put water from the moon to then link it to what most of us care about, some people care about in talking space. And those who care about open biodiversity, we want to have confidence that these measurements will be measured by so being able to trace back to the light field is critical in that exercise.
Yeah, in moving through that sort of closure idea, I think Colin showed a diagram where she sort of showed multiple steps and arrows in the forward and inverse problem, right? In Andrews, yeah. So in moving in that sort of, in figuring out where you are and going from one position to another, it involves modeling, and you need this to make that model more accurate.
Can we talk at all about the uncertainty of what happens? Not yet.
Yeah.
These are the basics.
Does that answer your question? All right. Yeah, absolutely. Here's just another example. This is a different volume scattering sensor. This is one called Mascot, which is, you'll see if you read much about scattering. It's a more recent instrument that was designed by Mike Trudowski, who used to work at Wet Labs, which was became part of Seabird. This is just a fixed, it's got detectors spaced every 10 degrees, looking at scattering at multiple angles. They deployed Mascot in the surf zone off Scripps Pier, looking at just what the VSF looks like, or the phase function looks like when you've got waves coming in, bubbles, lots of aeration and waves breaking, sediment being pulled up into the water. And towards that idea of understanding what sort of information you can get out of this, so that biogeochemical side, can you use the shape of the phase function to tell you something about the particles? He did a pretty extensive analysis of this 90 minutes of data. And he found that he was able to pull out some distinct sort of shapes in his data. One was the background, which was just fairly low, normal phase function scattering. Petzold is this dotted line that you can't see very well. And then sediment is just sort of an elevated backscattering. And then for data where they verified that there was a lot more bubbles in the water, there's this actual like very distinct shape with a scattering in the 80 degree range, and that's just from the physics of the way bubbles scatter. So from this data, you can say something about, from the phase function, what are the dominant things happening in the water? Is it tons of sediment? Is it tons of bubbles? Or is it just regular sort of the water that was there before? So an example of the.
And notice this is not due to changes in concentration.
Yeah.
Concentration is being normalized.
Yeah.
Divided by total scale.
Yeah.
So this is the concentration independent.
Yeah, so the scattering function will tell us in general how much scattering there is, the concentration to first order. The phase function tells us the shape, which is due to the type of particle or what's going on with the physics of how that type of particle that's in the medium scatters. All right. This is pretty straightforward. Just like absorption, scattering coefficients, VSFs, they can be thought of as like additive properties. So if you have the volume scattering function of different components in the water, you can sum them together. If you have different backscattering components, if anybody's done any sort of like GIOPs or anything like that, you'll often see these decomposed where you have the backscattering broken up into backscattering of water plus backscattering of thing one plus thing two plus thing three in general. So that also works for scattering properties. I think Meg kind of showed it also for absorption yesterday too. You know, the absorption, total absorption's got the water components, the dissolved components, the phytoplankton, the non-algal particles. One quick little note is that if you're trying to do this with phase functions, you need to sort of weight them based on the amount of a given scattering, because the phase function has the scattering coefficient normalized out of it. If you want to add them together, you have to throw that back in as sort of a fraction of the amount of stuff that's scattering. So that's the VI over B. So just keep that in mind. What kind of components for absorption did you look at that, I mean, maybe would work for backscattering? Yeah. What else backscatters or scatters in general? Yes. Water itself, particles, bubbles, turbulence. If you have the right models, if you have the data, you have models the need to define it that way, you can define it pretty much anyway. Here, just kind of thinking of a normal way that we do it in a lot of arrangements like GIOP. You've got water plus phytoplankton plus non-algal particles, and then whatever else you want to think. If you're in the case of that Scripps pure data from Kordowski, he's probably got to think more of bubbles, sediment, water. All right, really quick physics, just connecting this to hopefully stuff you've seen before. The idea of having two media. You saw it in Playing with Light, I think, Snell's law, right? You shine a light or you shine some wave at a surface with a change of index of refraction, the beam refracts, right? It also reflects. And we can come up with a formula that connects those two. I think you did that on Monday. Ultimately, what it comes down to is this refraction phenomenon is the redirection of the wave when it enters a medium of different index of refraction. You can think of it, in this case, if we think of N2 being higher than N1, so a more refractive material, like you would typically have as a particle in water, or a water glass interface in an instrument. You can think of it as the wave being slowed down by the denser media. You can get very deep in the physics, and actually Mobley does a pretty good job of getting into the deep physics of like what the index of refraction is and why this is all happening. You can approach it with different physics, but ultimately the index of refraction is related, it's a material property, it depends on wavelength. It's the ratio of the speed of light in vacuum to the speed of light in that medium. It's related to this epsilon r, which is just it's a physical property of the material that's being looked at, related to the polarizability of the material. In ocean optics and a lot of scattering treatments, we're interested mostly in what we call the relative index of refraction. So it's the index of refraction of the particle relative to the medium. So you could think of that here. N2 was the particle surface, N1 is the medium. So water's got a particle, has an index of refraction around 1.33, and your particle might have, depending on how it's constructed or what it's made of, a higher index of refraction, 1.5, something like that. And so we would think of that particle as having a relative index of refraction of 1.5 over 1.33. Adding a little extra complication, but actually if you dig into the physics, that's really fun. If you look at the way the plane wave solutions work, is that the index of refraction is actually an imaginary number. And this imaginary part of the index of refraction acts to attenuate the wave when it goes into a media. So it just falls out of some really cool math. But if we think in terms of the absorption coefficient, it happens to be 4 pi over lambda times that imaginary part of the index of refraction. Diffraction. So kind of the next level college physics example is like slit diffraction. That's probably everybody in some sort of physics class did like the shine a laser or a light source at a slit or an aperture and trace the diffraction patterns on the wall. Or maybe you did it with Ivana's hair yesterday. Or I think somebody had something set up on one of the things that you could shine a light at it, shine the laser, and you can see a pattern on the wall. So that's diffraction. So particles are an obstruction, right? So if we think of a big particle, it's an obstruction to the wave of light coming. So it's analogous to a slit or an aperture diffraction. So in that case, you've got a wavefront hitting some obstruction or an aperture, and each point of that wavefront becomes a new wave. And we're observing it off in the far field. So we get to use what's called Fraunhofer diffraction, which is just a far field version of this. It makes the math a lot easier. I'm not going to go into the details of the math there, but keep that in mind. For a particle, what we often see as diffraction is this idea that scattering is happening much more in the near forward. So if we have an incident beam hitting a particle, we have all sorts of weird structures happening, but it's very heavily weighted in the near forward direction. And that's from diffraction. This figure is, I think, for a slit, and here's just kind of a plot of what that, or an aperture. And you can see it's got this sort of lobey structure where it's got a main peak and it's got some minima and lobes. That's the same sort of thing you see here as a function of angle. So here's 0 degrees, and you've got a lobe and these minima, that sort of structure. So they're analogous. Good.
Could you go back to that last diagram? I'm just curious, it's been a while since I thought about Fraunhofer diffraction versus.
Yeah, so Fresnel is in the near field.
Yeah.
So there's a general, I think it's Kirchhoff, which he and some other famous physicists of the era put together the general framework of solving this problem. And then there's Fresnel, I think Fresnel Kirchhoff, which is the near field when this is not true. And then Fraunhofer is a simplified case where this is.
Yeah, is there any cases in ocean optics, for example, where we would be using?
Not that I know You'd worry about that, I assume, probably doing some things like optical tweezers where you're looking at scattering off a particle very, very close to it. You do have to worry about near field sorts of effects if you do acoustics in the ocean. The wavelengths and distances that you're measuring put you in that regime for acoustics. But as far as I know, in the ocean, we're pretty much always in the front hopper. Yeah. All right, and then sort of the third physical phenomena, probably didn't have this in like high school or college physics, but the idea of Rayleigh scattering. And we kind of use the terminology a little bit sloppily. Kurt, I think Meg brought up a lot of Kurt's footnotes. Kurt has a great discussion, as does Bourne and Huffman, and they reference just this idea that people call a lot of different things Rayleigh scattering. I'm going to talk about it sort of generally as the scattering of some sort of dipole or charge element. So we could think of that as a water molecule, right? So we've got some sort of polarity in a water molecule where we have, you know, more negative charge here compared to on the other side of the molecule. Opposite. Yeah, more positive down here. But we keep kind of so yeah, so but the important thing is it's got a distribution of charge. It's not symmetric. So the polarizability of that dipolar molecule or element is the tendency for it to respond to an electromagnetic field. So you can think of this as, you know, two sort of, you know, I have it backwards, but a positive sort of element and a negative sort of element. And they're attached with a spring. And there's a certain strength of that spring. And that is the polarizability. So how hard do you have to move that with a field? How strong does the field hitting that, what we call a dipole, have to be to make it move? If we make a dipole move, it creates a field. So these charged particles that are moving, that are accelerating, generally have a characteristic field. And it looks sort of like this. And you can see them being pulled apart and put back together. And you're sort of creating this wave structure, and then you pinch it off, wave structure, pinch it off. So keep that in mind. What we're going to do is we're going to take elements like these dipoles and we're going to put it in a time varying electromagnetic field. So the blue line here is the electric field. Red is the magnetic field. We don't really care about that in ocean optics. But that E field, that electric field, is going to take that dipole, those two charged elements on a spring, and try to pull them apart and push them together. So it's going to make that E field, this field here, change over time as the wave is impacted. So that E field, what we would say, is sets up an oscillating dipole which generates secondary radiation. So like that first slide, we've got a charged element or a dipole or something. We're irradiating it, setting up an oscillation in it, and then it's re-emitting radiation. That's scattering. We think about this over time and think about what that dipole is doing and what's coming out of the particle. You know, we have our two little things connected with a spring and we're moving them back and forth, and there's that pinching off action. What happens is over time, you're making this emanating structure coming out of the dipole. So it's re-radiating electromagnetic radiation. Photon, wave. So we kind of are a little vague there, right? It's a photon, but it's also a wave. It's an electromagnetic wave that's hitting the dipole.
And then there's a reignition.
Yeah, which is a wave. Yeah. So the incident wave is moving the elements apart, and as they're moving apart, they're creating this electric field here. You can see as we move it together, we're creating a field, then it sort of pinches off, so it goes null. And then you'll notice that the charges go opposite. So now we're generating the field in the other direction. So we're generating a whole bunch of these emanating spherically out of that. Just conceptually. Yeah.
this is not a vibrating molecule.
Correct.
We're talking about yesterday. This is like the red and blue electron clouds I was showing you. Those are my.
Yeah.
That's what that. They're not really doing that.
It's, yeah, and it's interesting because, you know, it's models at different scales, right? So part of this whole dipole approximation is that this is infinitesimally small, because physics likes to do not stupid, interesting things like that. This is infinitely small, but somehow it represents the charge variability across a water molecule or some other molecule in vapor or whatever. But you know, we kind of think of it more as, in some ways, as a conceptual thing. And that's why we call this Rayleigh scattering. But I think if you want to be a lot more pedantic, Rayleigh scattering is like specifically molecular scattering in a gas. But because the same sort of physical principles work for small particles, very, very small particles relative to the wavelength, we still use the term. That's why I kind of at the beginning wanted to make you not too stressed out about nomenclature and the words for these models, because ultimately sometimes they're misused, and it's just the general concept is what is the takeaway. Yeah. Yeah. No, nope. So that's a great question, actually. So this is moving at some frequency or wavelength, right? In whatever media it hits the dipole. This is going to oscillate at the same frequency as this. So this will, in general, oscillate no matter what frequency. It doesn't have that quantum thing that Meg was talking about, where it has to be a certain amount of energy or wavelength to be absorbed. As long as if you come back here, you know, remember that these material properties are functions of wavelength. So like this ER, epsilon R, is related to that springiness of the dipole. It's how responsive that molecule or that dipole is to the incident field. So keep in mind that that's wavelength dependent, but here, as long as there is some index of refraction or some epsilon R for whatever wavelength or frequency that's coming in, this dipole is going to oscillate at that same frequency. It doesn't have to be some discrete frequency. It'll be at the same wavelength, same frequency. Some will have, yeah, when you get into that spring model, it gets real deep. If you ever had it in physics, like when you start putting things on springs and you have a forcing function, you get resonances, you get damped response, underdamped response, all these like very sort of common mechanical physical concepts have been modeled for these dipoles and the sort of structure of the atoms and the way they respond to electromagnetic radiation. I think it's the Lorenz model is one that's used commonly, and that describes it all. But here, as long as it is polarizable or has, you know, the property of being moved by the electromagnetic wave, it will move it at the same frequency. It doesn't shift it or anything. So this is elastic scattering. No change in wavelength.
The dipole being exposed to multiple different frequencies at once, so
Sure.
the through string of the dipole is to the position of
I'm sure there's probably a second order effect, probably where you can't move it, where there's limitation of that you can't have too many superimposed, or certain frequencies that can't be superimposed with each other.
Well, I'm curious if there's any when you start.
Yeah. As a function of wavelength.
Yeah.
Yeah. I don't know, man. I don't know the physics of that. Yeah. Yeah, but here we're considering it at one wavelength or one frequency, and the oscillation is going to be at that same frequency, and the re-emission is at that same frequency. But again, you could have red, green, and blue hitting that dipole all at once, and red, green, and blue is going to come out potentially at different strengths, but it's going to come out. All right, what does this look like just in terms of a phase function or VSF? It's pretty flat. You know, you remember we were looking at our VSFs with log scales on the y-axis. These tend to be pretty much closer to isotropic. This is an example of this is what the derived Rayleigh scattering function actually is. This is a plot of that from Mobley's optics book, where blue is the Rayleigh calculation for this formula. And then we'll get into me a little bit, but me is an exact electromagnetic solution for a particle. And this is just simulating those same index of refraction and size. And they're very similar, but I throw this here just to show you the structure is relatively smooth and flat compared to the other VSFs and phase functions we've looked at.
So the red one is specifically for particle that's 404 micron.
Yeah.
Where wavelength provided is 500. While the Rayleigh one is for, you know, the smallest particle you can get up, right? So,
Yeah.
That tells you that, you know, even for colors, you're starting to get some imbalances, changes.
Yeah. Where unless you know it's a Rayleigh scatter or you need the simplification, in general, computers are cheap. Computer speed is cheap now. Me theory is easy to run.
And yeah,
It's more exact.
Now, if you consider the Rayleigh, the only thing that changes is not the shape of the set, it's only the magnitude. As the diameter goes up. And the shape is independent. The angle is independent.
Yeah, got this 1 plus cosine of psi sort of shape. Another key thing from Rayleigh scattering is this inverse wavelength to the fourth. So the wavelength dependence of Rayleigh scattering follows that. And so you'll see that with other small particle scattering, this very steep lambda to the minus. This is why the sky is blue.
Much more scattering and molecule.
Another way to think of it is it's a solution to Maxwell's equations that govern electromagnetic radiation for a homogeneous sphere. So it's a plane wave hitting that sphere, setting up boundary conditions, and doing this horrendous amount of math in 1905. This amazing feat that he and a couple other people around the same time managed to pull off. And these approximations like Rayleigh, for example, you can actually pull out of that math by looking at simplifications here and there. For example, me is this, it's a big series of things, of functions that are put together. If you only look at certain elements of that series, you can kind of simplify it down.
And maybe it was 19th century.
Yeah.
But it's a particle much more.
Yeah. It was around when Tyndall was also trying to figure out why the sky was blue, I think. Okay, so thinking about that dipole scattering, just really quick general concept of scattering by a particle. Again, we have single particle here, and we've just kind of showed it arbitrarily, but we divide it into these dipoles. So now it's not a molecule or anything, it's some element of that particle that we can think of as having a charge separation or some distribution of charge. So we pile those all together into an arbitrary particle right here, hit it with an incident wave. Each one of these guys is going to re-emit a wave. So if we put an observation out here, a lens that takes all the wavelets hitting that lens and focuses them down to a point, we'll have a certain amount of phase information that's a part of each of these wavelets, the wave. For a small particle, those scattering elements are going to be really close together, and the phase is going to be much closer to each other. So they'll be close to in phase by the time they make it to your observation. The bigger the particle gets, the more likely they are to be out of phase, and the more constructive and destructive interference that you'll have as you move your observation around the particle. inseparable. The great explanation of this, Born and Huffman, first chapter, going through the idea of like this general concept of scattering.
And we do a rebound.
Yeah. Yeah. That'll be exciting. That's good stuff. Yeah. And thinking about this general concept as size changes, you know, when they're really small and the dipoles are much more in phase, the scattering is pretty isotropic. As you get bigger and bigger, you get more and more constructive interference and lobes and such. And as you get bigger, more structure in the particle size, and then the particle scattering rather. Okay, so this was from that microscope on Monday. So some marine particles from the river out here. I think that's pretty cool setup.
Those students who were here were last early.
Yeah. Yeah, we
The rest of you were great.
yeah, it's really cool. But thinking more generally about scattering in the ocean and the particles that scatter, you know, what parameters are going to define the scattering? Like, how do you model this? What's that?
It's like an homogeneous sphere.
It does, right? So many, like, this guy's at least almost spherical, or maybe at least round. At least it's not the whole field of view in a stick. But it's certainly not homogeneous. That guy's maybe a little closer. That might be, I don't know. Like, what are the important things that, like, from these different physical phenomena that we've talked about that will affect the scattering? Size. Okay. Can you say anything more about the size? Are all 200 micron, like, let's say they're homogeneous spheres, are all 10 micron spheres going to change or scatter the same? Right. Okay. So index of refraction is going to matter because that describes how electromagnetic waves are going to propagate into the particle and through the particle. And one thing I'll add to the size is it's not just the size, but the size relative to the index relative to the wavelength of incident light. So all these phenomena are relative to that index or that incident wavelength. So in particle scattering, what we typically think of is what we call the size index. So that's this X here. These are the sort of key first order drivers of scattering. It's the diameter of the particle relative to the wavelength, and we throw a pi in there. And then the index of refraction relative to the medium, like I mentioned earlier. And again, these can be complex, but so the index of the particle relative to the index of the medium. You'll often see different people use M's, N's, N primes, kappas, all sorts of different things for index of refraction and complex index. But size relative to wavelengths and index of refraction relative to the medium. If there's like two things you get out of today, if there's three things, one, sort of the physical ideas of what makes scattering happen, like just that there's heterogeneity in terms of electric charges and matter, waves interact with that matter, re-radiate. So scattering equals, energizing and then re-radiating, and these two things. Like that's like, then we're done, but we're not. So we can use these to sort of look at some different regimes of scattering. In marine particles, we often say they're soft. And that just means that that M is close to 1. And that's true for most marine particles. Even what we would call harder particles like sediments, still a reasonable assumption. What does this row here, we won't get into it, but that's the phase change as the wave is going through a particle, how much that wave has changed phase when it leaves. That's important in some of these models. Won't get into it, but this is the different sort of particles over particle size, going from actual water molecules, dissolved in particulate stuff, whatever that means. Suspended particulate matter, different types of phytoplankton, plankton, bacteria, viruses, so spanning huge size range. Our dimensionless size parameter X equals 1 for 600 and something nanometers, so red illumination puts a square in here. So smaller particles than 1, larger particles than 1. And then there's these words here, Rayleigh, we kind of went over that. Rayleigh-Gans device, Van der Waals geometric optics. Those are just different approximations to scattering formula that you can find. They're simpler than me theory, but other than geometric optics, maybe even geometric optics, they can all come out of the me theory as simplification. But the other thing to think about here is, just use me theory. It works for any X and M. An exact solution for homogeneous spheres. So as long as you keep that limitation in mind. One quick look at connecting those big physical principles to me theory. So we have some particle. If you think about what's going on in that particle, you have rays hitting the particle. You get transmission, refraction, reflection, and diffraction around the particle. This is a figure from Kirk, which is a great resource. Looking at summarizing some data from a couple of papers, looking at scattering angle and the strength of scattering. In this model here, they've modeled the particles as just having a transmission and reflection component. So only accounting for that type of physics in the particle scattering. This guy here, the dashed line, adds diffraction. So that near forward scattering, so stuff going off this way. Me theory is the dark curve. And you'll see, so that's the exact solution. For a homogeneous sphere, that's what we assume is correct. And what I think is really powerful about this figure is you take these basic unrelated physical principles of diffraction, which we looked at like it's an aperture or a disk or a slit, and Snell's law through the particle. You add those together, and you've accounted for most of the variability that you see when you do the exact solution. The exact solution is Maxwell's equations, hardcore physics, exact solution. But looking at some of these approximations, we can get really close. And so they're different phenomena, but they get you to the same result. And I think that's powerful in scattering. You can look at physics in general, but scattering, you can look at a problem in a lot of different ways.
Zero scattering forward.
Yeah, straightforward. Pi is straight backwards. But we don't show that here.
And the reason the presentation are important is because they have a much simpler dependence on parameters such as size and relation size to wavelength and reflection, and they allow us to build an intuition that we cannot if we just stare at Maxwell's equation or at we have nothing to work with. Right?
Yeah.
But if you want to understand why we're forward scattering most of the time on size and not that on composition, these approximations is really useful.
Yeah.
And that then gives you a instrument like this that gives you size division based on your forward scattering without having information on composition. The one that why does it work? Why not they're not the same size? No, it works because in this limit of the fraction, composition is much less important.
Yep.
So all those values are used.
So quick me slide. So me theory's basic idea, Emmanuel tells me, a size parameter and a relative index of a fraction. And you put that through your me code and you get a few things out. You get what we call a cross section. So this is the absorption cross section and scattering cross section. And then these amplitude scattering element matrix elements that describe the polarized scattering as a function of angle. Not going to get too into this, but you can arrive at the phase function from looking at those. And then these are connected to the IOPs A, B, and C. So these cross sections are basically the amount of light that's removed according to that phenomena, either absorption, scattering, that relative to the cross-sectional or shadow area of that particle, like the projected area of that particle. We can also, sometimes MATLAB codes will have efficiencies, which is just the fraction of those two areas that comes out of it. We'll do a lot more of that. I think both Meg and Emmanuel talk a bit more about cross-sections, efficiencies in looking at particle properties and such, mostly Emmanuel. And then we'll do the me theory lab that will get you very deep in these settings. And I like to throw this up too. We talked a lot about modeling. So Born and Huffman very important book on particle scattering. He had this other paper where I think he was just being kind of grumpy and wrote an article, editorial in a journal, where he was just kind of tired of people applying models that are not applicable. So I always thought this was kind of fun. I mean, I could read it. We criticize using M theory where applicability is dubious. Modelers sometimes say they know that M theory is inadequate. They know their system's not homogeneous spheres or it's not applicable or something, but they do it anyways. Because it's the only game in town. Better to do wrong calculations than do none at all. Modelers have to model. So their takeaway from this paper is an alternative, not modeling, until like adequate methods are at hand. So I always keep this one in mind. I think it's kind of fun.
We have several of those and
Uh,
the beauty is that you tell that it's not,
Yeah.
it's not shy of expressing its activity. Obviously, the argument.
Yeah.
And it's phenomenal.
Yeah.
Which is somebody telling us in the face of people. God, why are we continuing to do something that makes sense?
Yeah.
It's really fun. I don't know.
Yeah, it's a fun read. All right. But continuing on with modeling, I just wanted to talk briefly about how you connect those cross sections to the bulk IOPs. So again, we have these cross sections. They're functions of the size distribute or a particle size and index of refraction probably. They have a dimension of area, unit of area. And that's what M theory is going to give you, or Rayleigh or Van der Waals. Any of these models are going to give you the cross section. That cross section is for a single particle. But we don't generally work in single particles. In the ocean, we have huge assemblages of particles, right? So lots of them within a certain volume. So we can think about that as just the number of particles n per cubic meter. Since they're additive, it's really as simple as taking that cross-sectional area and multiplying it by the number of particles with that cross-sectional area in that volume. So n, as we said, was meters to the -3. The cross-section is an area. And again, just checking the dimensions, we get inverse meters. So that checks out. So that's the simplest case where you have one particle type, some known concentration. More realistic is assuming that we have some size distribution. We call it particle size distribution. This is the number particle size distribution, ND. And the basic definition of that Meg will get into is that NDDD is the number of particles per volume with diameters that are in a bin between D to D plus DD. So number of particles in that particular size bin per volume. And we just do this, we formulate this just slightly differently. We now integrate over diameter. We throw the size distribution in there, throw that cross section in again. Looking at the units, just again, it's these are typically per volume, per width of size bin. So it's often noted as per cubic meter per micron. And then again, an area, and we got a micron there. And so we get the same unit. So just checking those out is always a great sanity check. We like to see papers and analysis with units. So that's how you connect those single particle properties to the bulk IOP measurements. Oh, sure. So this is the absorption cross-section and scattering cross-section. So this is the equivalent area representing the energy that's removed by absorption. And similarly, this one for scattering. So how much, I mean, if you think of a particle just attenuating light without getting into some stuff, it's blocking the cross-sectional area, right? So in reality, a particle is not totally solid usually. So only a certain fraction of that is going to actually get blocked or absorbed or scattered. So that's that area, the equivalent area. You can think of the efficiencies down here as like sort of the probability for that given particle size that it's going to get absorbed or scattered. So yeah, again, this just connects those single particle properties that we get out of me theory to the bulk. All right, just briefly, the power law size distribution. We've defined what ND is. So it's really common to assume a power law size distribution. You see it frequently in ocean optics. This is a figure that represents different types of particles in the environment. And roughly those particles, if you fit a line to it, follow this ND goes something like diameter to the -4th. But in reality, you do see variability in that. But often we'll just go ahead and approximate that variability by changing the steepness of that size distribution slope. Just a first order kind of thing we do. So typically in the ocean, we see that going from about, flattening out to like ND goes about diameter to the -3, or steepening to the point where you have diameter to the -5. So what that means, this guy here is very heavily weighted towards small particles. This one is going to be weighted to bigger particles. So it's just kind of getting that relative, how much small particles versus how much big particles. Are you going to talk about that also in, you do it obviously in P size distribution, but for beam C and gamma? Okay. Stramsky, yeah. Yeah, Mobley grabbed it from Stramsky, I think, and reworked it. Yeah. Yeah. So equivalent particle diameter is here on the x-axis, and then this is the concentration at ND. So the number of particles per volume in some finite or infinitely small width here. So the number of particles per size. And so at this region here, would imply that for this size here of about 0.1 micron, you've got something like, I think that's 10 to the 14th particles per cubic meter for that micron size thing. Does that make sense? Oh yeah, right? There's not I don't have an answer to that.
I think you're involved.
Yeah. I think it is, yeah.
It's a matter of like a sphere.
But that's an incredibly important question to ask. Yeah. The question was what this equivalent particle diameter means. As you guys saw, particles in the ocean are not spheres, generally. So how do you represent these? How do you represent that in a particle size distribution? I think Meg will probably talk a little bit about equivalent spherical diameter and things like that. Yeah, so if you work in the space where you're looking at particle size and particle size distribution, you should always be keeping that in mind. Because we generally, to plot them, have to make some assumption like equivalent volume sphere. So the diameter, if you have a chain or cylinder, what is the diameter of the sphere that has the equivalent volume?
What's the size of this?
Yeah.
How can you use a single parameter to describe the size of the diagram? You can, you have to explain how you do it, and then you have to explain why that's the
and the other important thing, I mean, I will, frequently criticize that sort of, trying to make things into equivalent spheres, but ultimately the reason we do this is to come up with like first order approximations, or can we model the general behavior of a system? So even with this, this is a simplification of the global ocean over all time. We roughly see this power law diameter to the -4th. You go to the coast, it's not going to be that out here, probably. It's not going to be that on your cruise. It may not be represented by a power law very well at all. It may be, it may have bumps on it because there's a balloon. But in general, this just gives us this idea that we have a lot more small particles than we have big particles per volume.
And the sun is huge.
Yeah.
For the particles.
Yeah. Was that 4 or 5 orders of magnitude? And then, yeah, and spanning.
I mean, this fire family itself, and you know, you go from 0.5 microns to millimeters. That's 3 orders of magnitude. So for things that are not usually departing from sphere, size still has a negative. Because there's still a big difference between the icon and local compass. And
But yeah, again, keep in mind, it's more or less a general idea, and we're just trying to get overall behavior of a system. Going back to how we got the bulk properties. So this is beam attenuation now. So scattering plus absorption. And similarly to the CX and CABs, we have CX, which is the extinction or attenuation cross section. And I just kind of wanted to throw this up to show you how we can connect this power law size distribution to an IOP. So we have that same integral where we're going over the size distribution, the power law size distribution, and the combination here of d squared and qx is the cross-sectional area. So I just switched it to a efficiency and an area. And then if we, instead of working with diameter, work with the size parameter, so that diameter relative to the wavelength. Do some variable substitution, like we now our size distribution doesn't go as d to the minus mu, it goes as sort of lambda x to the minus mu, mu being this slope, that -5, -4, -3. Qx we have in terms of x, diameter squared goes as lambda x squared, just by these substitutions of what the size parameter is. And if we factor that out, we'll see that, you know, we can come up with this factor out here that doesn't depend on x. So we separate it into this wavelength term, and then a term that's the integral over size. So, you know, we could do this, but the important takeaway here is that something like beam attenuation, if we assume a size distribution that's got a power law, we're going to have some variability spectrally in beam attenuation that also has a power law, and they're connected linearly. So Emmanuel will talk about a gamma, which is when we model the beam attenuation as a power law of lambda to the minus gamma. And so that gamma is connected just with these basic concepts to the size distribution. This is kind of a big, heady concept. It's mathy, it's got a lot of integrals, complex, but the takeaway here is we start with this idea of our individual particle properties. We have a size distribution. We can make a few assumptions about our size distribution, and we can pull out the idea that we have a spectral behavior in that IOP. Make any sense? Sure. The size parameter. This guy. So the ratio with a pi factor ratio of diameter to wavelength.
And it's wavelength in the medium.
Wavelength in the medium. Yeah.
So what you call green.
Yeah.
Because green in the air.
Yeah.
In the medium is the medium.
We're in a sense a little bit at a disadvantage in ocean optics because we're always working with wavelengths, whereas a lot of times in physics, looking at it, it's easier to consider the frequency. Because things like that wave that are entering a different medium, the frequency is staying the same. But the wavelength is changing because the index of refraction is different. The wave is slowed down, it has the same frequency, so the wavelength has to change in order to compensate that. Okay, so that's just that general connection.
But it's not just that, yeah, the frequency does not change for the substation. But if you work in atmospheric science, what you see green is when it interacts, if the wavelength that interacts with the cloud of the neighborhood.
Yeah.
In the ocean, what we call green is green air, it's not green water.
Yeah.
In terms of the wavelength is shifted.
Yeah.
Is by 25%.
Yeah, but it's also an interesting problem because you can't observe that color in the medium. Because the minute exactly. So you have to keep that in mind, keep it in your pocket, but like, it's not like you're going to see the particle look different. Yeah. Keep in mind. So when you shot the laser beam at the surface of water looking at Snell's law, right? There's a red laser outside of the water, and when you looked at it, it was still a red laser. In the medium, it was not red. But you can't observe that. Because the minute you put a window or something in there, you've gone back to air.
So in your brain is always the color within the medium of your eye.
Yeah.
So that sort of translates back to whatever the image is like.
Well, your eyes respond to frequency.
Yeah, that's what I'm thinking. So imagine, I mean, why would you call it?
Yeah. All right.
It's interesting.
Yeah,
Many people who want activation. They see the
and it matters.
The size of the particle in all these statistics, there is
Yeah.
and it has to do with the size of the particle, the size of the, just like a drop.
Yeah.
But the wavelength, the sound gets in the drop depends on the size.
And it matters in the,
Ground rule.
it comes into play if you're, thinking about a wave that's going into some particle that has structure. So there's an index of a different, like an organelle and a phytoplankton that's got a different index of refraction. Let's say it's absorbing radiation. What wavelength is it absorbing? What wavelength went in to the particle? What was the change of wavelength when it went through the particle to get to that chloroplast? So it's cool stuff. Just finishing this up real quick. So we came up with this rough idea here that there's this power law dependence. So this is data from the Tara, the first Tara cruise, looking at beam attenuation as a function of wavelength. Turns out it is pretty darn smooth. You just don't pay attention to that. That's another story. And if you fit the power law to these spectra, like this was all across the globe, and you look at the histogram, this gamma, this slope, turns out it's pretty close to what you would expect for that -4. That d to the -4, because that should give you a gamma of 1, and it does. Pretty cool. So if attenuation is a smooth function, what should the spectral shape of scattering look like? Scattering is attenuation minus absorption. So Meg showed a lot of spectral absorption plots yesterday. And think about probably the easiest, I think this is Meg's data. So this is absorption by non-algal particles. They tend to be smooth as a function of wavelengths. So if beam attenuation is smooth and A is smooth, what would you expect B to look like as a function of wavelength? Smooth? Yeah, so keep that in mind. So something like non-algal particles will give you smooth. Conversely, think about absorption of phytoplankton. So I don't know that Meg showed too much in the way of absorption of phytoplankton, but it's all pigments, right? Chlorophylls and such. So that's got a lot more structure. So similarly, what do you think the scattering due to phytoplankton is going to be if the absorption has these strong spectral features? So if C is smooth and A is this, and you take this and subtract it from this, you're going to have structure, right? So just throwing up some additional data as an example, this is that same cruise, that Tara cruise, where here's the absorptions for sort of different water types based on chlorophyll ranges. And this is the beam attenuation I just showed you. These are the normalized versions of that. Here's the scattering. So depending on what your absorption looks like, sure, you see that these are from ACS data like you were looking at yesterday, and you'll look at particle absorption in that today. For this strongly structured absorption, your scattering has spectral shape to it. But when you get into more flat situations, you have much less. This is some old data from Bowdoin, where he looks at the same sort of thing with an AC9 for different water types. These two water types are more open ocean, where the absorption is going to be more phytoplankton-like. These are water types that are either case 2, so-called case 2, or more dominated by minerals or non-algal particles. And you don't see that same strong, obvious absorption spectra like you do there. I think that's kind of an interesting story. I just throw this up there. This is another case of going from sort of individual particle measurements to the phase function or volume scattering function. This is very mathy. It's a great paper if you want to read some crazy math by Fournier and Ferrand. But basically he takes the same idea of making an IOP, the phase function or volume scattering function, out of things that come out of our model. Here's the scattering efficiency, and then this is basically a per particle phase function. And you have that same wavelength dependence, but he does all kinds of simplifications to figure out what to use for models for the Q's and the P's to make it work out really well so that he can take the integral and end up with, yes, this is actually a simplified model for the phase function right here. But it works really well. It explains a lot of variability we see in the ocean. If you do any work with hydrolyte or radiative transfer, Monte Carlo, you're likely to see Fournier Ferrand as well as Petzold. So I just wanted you to see that. It also has a convenient thing where there's a nice expression for the backscattering fraction.
And as you see this, if you go back, the function that you use, that you decide to use.
Yeah. Yeah.
This is the power law.
Yeah.
And it's a function-
Oh yeah, sorry, I didn't say that.
It's a function of n, so the delta, u and delta on the bottom too.
Yeah.
And the delta has community fraction. So you know something about the kind of part of the
Yeah.
Something about the size of the
Yeah. So this is an assemblage of particles. So it's a size distribution, an assemblage of particles. I think I had the mu and index of refraction inputs. I think I deleted it. Yeah, so you'll see this. This is just some examples of what it looks like. Recalling what the phase functions look like. It's got that same peak near forward structure. The red curves here are Fournier-Ferrand approximations of VSM measurements. And it's pretty good. There's some issues in the back. Green is Petzold. So it reproduces a lot of the shape that we see in the environment. So it's pretty important. Real quick, I just want to tease you a little bit with polarization, because we're not going to talk about it much here. I think Patrick might give a lecture. But this is like very kind of where the community is heading in a lot of ways, because there's a lot of information we can get by using polarized light. So thinking about that wave that we had before, we've got an E field vector that's changing over time and space. So when we say polarization, we're just talking about sort of what shape this E vector is tracing. So for linear, this would be, I guess, what we would call vertically polarized polarization. The E vector is just stuck in this plane going up and down. It could be in a plane going this way. It could be in a plane going this way. Coming out of the sun unpolarized. It's all over the place. Random. It can go in a circle. It can go in an ellipse. There's all kinds of different ways that we can look at polarization. And one of the ways we quantify that is the Stokes framework or Stokes vectors. So this is the idea where we have some incident intensity or amount of energy that's in the electromagnetic wave, but then we throw a vector here that characterizes the polarization state. So for horizontally polarized, we throw a 1 here. This first element is just the amount of energy, the unpolarized intensity. So unpolarized light would be 1, 0, 0, 0. Polarized this way, this is a 1, this way -1, and so on for different types of polarization. In scattering, we look at the VSF. VSF is unpolarized light going in, looking at unpolarized scattering. When we have this amount of stuff going on, we have to treat it much differently. So here we think about that same beam being scattered, and we put 2 filters here, 2 polarizing filters, kind of like you did with the tank in the lab. So we can put a filter on the light going in, and we can decide what we have for polarization going in. So we can make this linearly polarized like you did in the lab. Your observation of scattering, you can put a polarizer there and look at the polarizer there, or the polarization state there. But ultimately what it comes down to is we can have these vectors, called Stokes vectors, that describe the polarization state of the light in the system. So we have some Stokes vector going into our scattering and some coming out. And the way those are connected is what we call a Mueller matrix. And this is those aren't there, you know those. This is a simplified version of the Mueller matrix for randomly oriented particles with symmetry. But just thinking about what these elements mean, looking at the matrix math, well, M11 is the unpolarized connecting the unpolarized. So that's just our VSF. But then we can think about, M12 and M21 are like the idea of we have unpolarized light getting polarized, linearly polarized. And we can come up with a quantity we call the degree of linear polarization. And this is some simulations figure I got from Mike Twardowski, looking at the sort of the space where we can plot degree of linear polarization for size distributions with power law slopes. So power law size distributions as a function of angle. So each one of these is like an angular plot. And the big takeaway here is that assuming it's a sphere, we've got some structure, but if we use some different model like a randomly shaped particle here, asymmetric hexahedra, for example, it looks a lot different. So there's information in this. So like we were talking about using the shape of the phase function to say something about composition of particles, there's a whole other world where we haven't even gotten into looking at information in the polarization. So not a quantitative idea here, just this is the kind of thing that we're moving towards as the ocean optics community. Really cool. It's a good time to be alive. All right, big picture. VSF is the effects of all the simple, complicated physical models that we went through. It's got all the phenomena: reflection, transmission, refraction, diffraction. It could be Rayleigh, it can be me, it can be geometric optics. But it's got all that information. Depending on the scale of your problem, we looked at a few different models. Large particles, diffraction might dominate. Small particles, Rayleigh might dominate. Me theory covers the whole range. So we can use different models. Another key that we kind of got at was that the magnitude of the VSF, or the scattering coefficient, depends on the type and concentration of the particles, and the shape or the phase function has information about the particle size, the shape, the internal structure, composition. We talked a lot about scattering coefficient in VSF. That's all unpolarized, but there's a whole other world of Mueller matrix and polarized scattering and polarized optics, where we have to treat this complexity a lot differently, like matrices instead of just scalar quantities. And I guess finally, a common assumption we make is isotropic media, randomly oriented particles, so that we can have a nice convenient scattering function. But there's assumptions there. If you're working in an environment with flow, maybe we violate that assumption. So that's it. Other than if you want to learn more about scattering, so I think Meg showed the ocean optics book. This is an absolutely gem of a resource for scattering, absorption, everything, radiometry. It's like Kurt and several colleagues' brain dump. It's amazing. Specifically for particles, these three guys are on your bookshelf. Different levels of treatment, different kind of attitudes. This is Bourne and Huffman right here. So this is the guy that said not to model. And the prose in there is really good, excellent explanations of things. The downside between, for example, these two books is that they deal a lot more with general particle scattering. So aluminum spheres in the atmosphere, or aluminum spheres in, perfectly absorbing medium. So there's physics that we work with a much narrower set of physics in the ocean for our particles. And so this Jonas and Fournier, that's Fournier is in the Fournier-Ferrand. This covers more of the marine situation. So, yeah. Oh. So Colin sent this earlier, just another great example of scattering. New York with the fires, like what's the atmosphere like? So this is from 10 a.m. to 1:53 p.m. So like just the change in time of scattering in the atmosphere. And you see it going not only blurry, hazy, but changing color, right? What are the particles? Just so think about this, lunch in the afternoon, or maybe when you're sleeping. Why did it turn red?
Guys, let's try and do that at 10:30 if possible. Or something great, something good.
Charlotte, what do we do here? Absolutely.
It's about the last part,
Yeah.
the composition. So we can differentiate like phytoplankton groups based like thinking about the morphology and everything based on the scattering angle.
Maybe. So, shape, there's a little less information. So there's a good review by Clavano that talks about shape effects on IOPs. The scattering function is going to depend more on size, but there are like for bubbles, for example, the same size bubble because of the construction of the bubble will look different in terms of ESF than the same size, phytoplankton sphere.
Yeah, because thinking about phytoplankton has so many different shapes. So I don't know. Which is the article that you said?
1 second.
Okay.
Hey, Charlotte, how do I? Just, oh, there you go. And
Yeah, you can press stop line.